Hey everybody, my name is Dr. Aarran Shaw. I'm an astrophysics postdoc at the University of Nevada, Reno, and I'm going to talk today a little bit about some of the research that I do that involves the Great Basin Observatory. Before I dive straight into that, just a quick bit of background on myself. I was born and raised in the UK. I did my undergraduate degree in physics with astrophysics at the University of Leeds. After I graduated, I moved down to the University of Southampton to do my PhD. I got my doctorate in 2016, and then I moved to Canada to start my first postdoc position at the University of Alberta in Edmonton. And I finished up there in October of 2019, which is when I moved down to Reno to work alongside Dr. Richard Plotkin in the physics department at UNR. And it's here in Reno that I've come into contact with the folks at the Great Basin Observatory. So one of the types of astrophysical objects that I'm interested in particular are what we call cataclysmic variables, or CVs for short. So what these are binary systems, so a system of two stars. One of the binary components is a normal sun-type star, and the other is what we call a white dwarf. Now, a white dwarf is the remnants of a dead star. It's what will be left behind when our sun dies. It'll shed its outer layers and leave behind the hot core. And that hot core is what we call a white dwarf. Now, in these cataclysmic variables, or CVs, the normal sun-type star, the mass from that star is actually falling onto the white dwarf, and it forms a disk around the white dwarf called an accretion disk. Now, these accretion disks are quite bright in X-rays and optical and UV light. And studying the light that comes from the accretion disk actually gives us an insight into the process of accretion, which is still a fairly poorly understood process. Now, there's a particular subset of these CVs called intermediate polars, or IPs for short. And the setup is basically the same. You have a binary system with a white dwarf and a normal star, which is losing mass onto the white dwarf. And the only difference is the white dwarf is extremely magnetic. So what this does is it actually disrupts the accretion disk such that matter actually has to flow along the magnetic field lines onto the surface of the white dwarf. IPs are, again, very bright in X-rays, in high energy X-rays, as well as optical and UV light. And they're actually, because they're pretty bright, they make really great targets for something like the GBO. One of the things that astronomers have recently noticed about some of these IPs is that some of them enter what we call a low state. Now, what this means is that they will be kind of happily sitting at a normal X-ray brightness, and then seemingly randomly, the X-ray brightness or flux will just drop into one of these low states. And these low states are quite poorly studied. The reason behind that is because we don't know when they're going to happen. So to truly understand what is happening in these low states, we need to point X-ray telescopes at them to see if anything has changed in the accretion disk. Now, we can't just point X-ray telescopes randomly at IPs and hope that one of them is in a low state. X-ray telescope time is extremely expensive, and we need to be as efficient as possible with it. And also, there are only a few X-ray telescopes currently in orbit, and other people would like to use them for their research as well. So we can't just point X-ray telescopes at IPs randomly. We need to be sure that something is in a low state before we can use the X-ray telescope. Now, how do we do this? Well, luckily we've noticed that at the same time as the X-ray drop in brightness, these IPs also drop in optical brightness. So the X-ray flux will drop, and at the same time, the optical flux will also drop. So this is where the Great Basin Observatory comes in. So a team of us at UNR, including myself, Dr. Richard Plotkin, and student Alexis Tudor, have developed a monitoring program of IPs to see if we can find some of these low states. So the idea behind this is we get the GBO to take nightly images of our target IPs, and we look for these drops in brightness. Now, if we see a drop in optical flux, then we know that the same will have happened in X-rays. So what we can do then is we can trigger a program that we have in place with the XMM Newton telescope to take a long stare at X-ray energies of one of these low states. So the GBO is really an integral part of this research program. It will enable us to inform deep X-ray observations of an IP in a low state. And observations such as this are very, very rare indeed. So we're really grateful that we have such a great optical facility that we can access. And I'm really looking forward to the results rolling in. So that's probably enough from me. I really enjoyed talking to you all. Thank you very much for watching, and I hope you enjoyed the video. Thanks very much. Goodbye.